Okay, what we are now doing is basic techniques of design and analysis of algorithms. Number one, divide and conquer. And for example, we studied the shortest, closest pair problem. So we are given endpoints on Euclid space. And your job, your task is to find the closest pair, like this. Okay, naive approach. Would be to check all the pairs. All the pairs. That means we need to check and choose two pairs that needs n square time. This is naive approach. Just we check all the pairs, all possible pairs, then of course we can find the closest pair. This is not a very obvious approach, but we need n square time. But if you look at this point, then you immediately notice that it is stupid to check, for example, this point and that point, this point and this point. Obviously, it's useless. Okay, but important thing is it's not so easy to find some systematic way of excluding those obviously not closest points. Of course, human's eye is genius. So if you look at this situation, then of course you obviously know that this pair and this pair, this point and this point are not closest. But in algorithmic viewpoints, it's not so easy to exclude those kind of useless pairs. Okay, that's why divide and conquer comes in. So what we do is to divide these points to SL and SR, and what we do is shortest, closest. Sorry. We divide endpoints into two groups, SL and SR. Then we obtain closest pairs from each region. Of course, by using equation. Okay? Then, this is the divide part, and the much more important is the conquer part. Then, by doing this, now you have a nice way of excluding obviously non-closest pairs. That means, what now? Now you look at one point, then you can squeeze the possible points. The pair, your pair, from n to only 6. From your possible pair might be all other n-1 points, but you can reduce the candidates from n-1 to only 6 by doing this. This is a really, really good, clever idea. So by doing this, the final computation time is n times log n. That is much, much better than n squared. So just please figure it out by yourself. Why we can reduce the possible number of points of your pair from n minus 1 to only 6. That is a really, really great thing of this algorithm. Okay, good. Number 2 is a dp. Dynamic programming. Again, this is very clever. So what you do is just exhaustive search. By using tree structure. Okay. However, if you look at some level of nodes, then you notice that there are many same ones. Same nodes. Many same nodes. So the size of this tree is something like 2 to the n, or 4 to the n, even 4 to the n. But if you take a close look, then you notice that there are many same points. Okay, so just you combine those same nodes into one, then the complexity gets down from this exponential number to just something like n square or n cube. A great improvement. Okay, this is a DP. So this is also very great technique. However, unfortunately, dynamic programming does not work always. So this kind of speed up might not be possible, but it's still good. It's still valuable to seek some kind of a speed ups that is an exponential speed up. Meaning, for example, 2 to the n to 2 to the n over 2. This is it's exponential speed up. Actually, we also can write this is a 1.414 to the n, because it's a 2 to the 1/2 is just square root of n. That is 1.414. So this is also this. The idea is to reduce computation time from 2 to the n to some small number, small constant, 1 point something to the n. That is exponential speed up. Okay. Or maybe this might be a bit more, something like 2 to the might be a little bit more, 1.414 to the n times something like n squared plus n plus 1, something like this. So usually we have a polynomial term, we have a polynomial coefficient like this, but we usually ignore this kind of polynomial. Ignore. Why? Because this is as you see, this c to the epsilon n. This can be written c to the epsilon n. I would say this is at most c to the epsilon n when n is large. Asymptotically. Okay? So that means this whole thing can be written something like 1.4, yes, 1.414 plus epsilon to the n. Okay? At most. At most. But you can choose epsilon as small as possible as you want. That means we can just neglect this epsilon part. So we usually say this complexity, this is we usually ignore this kind of polynomial term, polynomial coefficient. Okay, so we just say speed ups from 2 to the n to the 1.414n. Maybe with some polynomial coefficient, but we ignore it. Okay, good. Today, we're going to study two standard techniques for obtaining this kind of exponential speed ups. Okay, that is backtrack and local search. Okay, so I'll show you the two basic techniques for getting exponential speed ups. Now, today's example 7. I hope the number is correct. It's a called 3SAT. SAT is satisfiability. Three satisfiability. Okay. Given 3CNF formula. What is 3CNF formula? That's a Boolean formula. Looks like this. F x1 3 x4 2 Okay. So we are given a Boolean formula. It looks like this, which looks like this. That is called 3CNF. CNF stands for conjunctive normal form. Conjunctive normal form. Conjunctive normal forms means formula is a set of clauses. So we call this clause. And each clause consists of at most 3 literals. So we call those things literal. Literal means variable, Boolean variable, or its negation. This is negation. Bar is a negation. Okay, probably you already know this kind of Boolean formula, I hope, but this is not very difficult. Just a Boolean formula. So given a 3CNF formula, looks like this. 3 means, as I said, at most less than, at most. At most 3 literals. So this 3 comes from here. Okay? So we are given 3CNF formula, F, which looks like this. Our question, question. I would say this is a question is better. Okay, the question you have to answer is F is F satisfiable. So your answer should be yes or no. What do you mean? Do I mean by satisfiable? That's pretty simple. So this is a simple example. X1, X2. Oh, I'm sorry. This sign, this operation is Boolean OR. This is Boolean OR. Bool OR. And here, this is Boolean AND. Boolean AND. Okay? Okay. So suppose that we are given this formula. Then this formula is satisfiable. Why? Because if you assign x is equal to 1, or x1 is equal to 1, x2 is equal to 0, and x3 is equal to 0, then f becomes 1. So because x1 is equal to 1, this clause is already true. It's 1 because this is Boolean OR. Okay? And this is also okay because here we have x1. And here, because we set x2 is equal to 0, this is okay. And here, yeah, we have two ones. So it's of course okay. So by using this assignment, we can make the whole thing true. Whole f true, or 1. Okay. So that is why we say this formula is satisfiable. So if you are given this formula, your answer should be yes. Then what kind of formula is unsatisfiable? What kind of formula is unsatisfiable? Okay, it's a simple example. Is something like x1, x2, x1, x1. Okay, this is a simple example. So that the formula is unsatisfiable because for any assignment, at least one clause becomes 0. Right? For example, if you use 0, 0, then of course this guy becomes 0, 0, 1, this guy becomes 0, 1, 0, 1, 1. So for any assignment, one of the 4 clauses becomes 0. That's why this is unsatisfiable. Okay. Now, okay, so I'll show you backtrack algorithm to check the given formula f is satisfiable or not. Well, that is just exhaustive search. Just exhaustive search. So we are given f, then just x1 is equal to 0, x1 is equal to 1. So we check two cases. So suppose that this is your formula. Then if you assign x1 is equal to 0, then this formula changes. This formula becomes a bit simpler. Okay, so for example, x1 is equal to 0, then this guy becomes 0. So f becomes something like x2, x3, and x2, x4, and okay. If x1 is equal to 0, then this clause disappears because it already becomes 1. So you don't care, the other parts. And so this formula disappears. So the formula becomes simpler. Okay. So let's say this is f1. Now this is f2 is equal to, I don't know, x2 to x4 bar, and so on and so forth. Now, we repeat the same thing. x2 is equal to 0, x2 is equal to 1, x2 is equal to 0, 1. So again, F3, F4, F5, F6, the formula becomes changing, continue changing, continue to change. It's getting simpler and simpler and simpler. Okay. Then the whole search tree, and somewhere, okay, now this is F, something like okay, F, 12,566 is equal to, okay, 1. Okay, you are lucky. Now you know that this formula is satisfiable. Okay, but maybe if this formula is unsatisfiable, then you can't get this kind of node. You have to go to the bottom. Okay, what it means, if you have n variables, then the whole search tree the size of the whole search tree can become up to as large as 2 to the n. Well, maybe there are many different kinds of things happens. For example, like here, it is f is equal to 0. Then of course, you don't have to go further. You can stop here. Then the backtrack means if you get to the node which is bad node, then you can just backtrack and then the different possibility. You go to different possibilities. That is the name backtrack, but you don't have to worry about that. The name is not so important. Backtrack means just this kind of a standard exhaustive search. Okay, so it means the size of the whole search tree can be as large as 2 to the n. Why 2 to the n? Of course, this is a binary search tree, so it's obvious. But if you would like to use recursion formula, then T of n is T of n minus 1 plus T of n minus 1. This is your recursion formula. Why? This is T of n. Then this formula and this formula is exactly one variable less. Okay? So that's why it's a n variable formula. The computation time of n variable formula is 2. Okay, 1, 2 of n minus 1 variable formula computation time. And this is a recursion formula, and if you solve this recursion formula, then you can get T of n is equal to 2 to the n. Of course, this is correct because you substitute here, then 2 to the n is equal to 2 to the n minus 1 plus 2 to the n minus 1. Exactly the same. So this is your answer. Good. I would like to reduce this search tree significantly. Okay. First possibility is, of course, DP, dynamic programming. But unfortunately, it does not seem to work. Why? Because the basic idea of DP is that suppose that you look at some level, then if you have many same nodes, then you can use DP. But unfortunately, probably you can figure it out by yourself. But we don't have any good property to reduce the number of different formulas in, for example, in some level. We have too many different possibilities for formula, so we can't bound the number of different formulas. Okay. This is a kind of a good exercise for you to figure out that there is no good bound. There is no good bound for the number of different formulas in each level. So unfortunately, you can't use DP. But so DP, probably no. Unfortunately, no. But instead, okay. But fortunately, we have some structural property to reduce this search tree. What kind of structural property? This is pretty easy. So again, I write this search tree F. And this x1 is equal to 1, x1 is equal to 0. As I said, here we have n minus 1. So n is equal to f, fn. Okay, and n is the number of variables. Here, of course, one variable less. Okay, so this is fn minus 1. Okay. Here, of course, this is one variable less. But if you look at the simplified formula carefully, then there must be clause of size 2. Okay. The simplified formula must have at least one clause which has only 2 literals. Why? Why? Because look at this formula. Look at this formula again. Okay. Now x1 is equal to 0. So, yeah, this clause becomes a clause of size 2. Looks like this. Okay? And also, this guy becomes the size of 2. Okay? This guy becomes, this disappears. Disappears. So, if we have this kind of formula, only this kind of formulas, then, we have no guarantee. We have no guarantee of clause of size 2. Okay? Do you understand? If you have this kind of formula is x1 appears positive, then we must have a clause of size 2. Understand? It's clear? But x1 appears negative, then this clause just disappears. That means we have no guarantee for this kind of clause of size 2. Okay? So suppose that if all x1 appears negative, then we don't have this formula. But in that case, of course, if x1 appears all negative, so of course we assign x1 to 1. No, 0. Okay, then of course that is very good. That doesn't use any generality. Okay, so you don't have this branching. You don't have this branching. That means you can reduce the number of variable by 1 without any, without losing any complexity. Okay? So that's why you can assume without loss of generality that the simply the formula has a clause of size at most 2. Okay, maybe you are confused. Just take a time. Just take a time. It's a very pretty simple fact. Okay, now then we assign x2 is equal to 1 and x2 is equal to 0. Then this guy becomes fn minus 2, of course. We already fix 2 variables. Then this guy has n minus 2 variables. Now, if we set x to equal to 0, then the formula becomes x4 bar. The formula has a clause of single variable. Then, again, it's completely safe to assign this variable 0. We don't need to check x4 is equal to 1. You don't have to check. You don't have to branch. Because if you assign x4 is equal to 1, then this guy becomes false. Then the whole thing becomes false. So you don't need this branching. And of course, you automatically set x4 is equal to 4, then this becomes fn minus 3. Because we already set 3 variables. Good. Then what is your recursion formula? What is the recursion formula? Recursion formula T of n is equal to T of n minus 1 plus T of n minus 2 plus T of n minus 3. So this is your recursion formula for the complexity of this algorithm. What is the solution of this formula? You can check it by yourself, but this T is something like 1.84 to the n. You can use your calculator or Mathematica, to solve this formula. It's pretty easy to figure out that solution is something like 1.84 to the n. Okay? Now it's much better than 2 to the n. This is exponential speed up. This is what I call exponential speed up. Great. Great. A bit more. Okay. I omit the details, but if you use a bit more careful analysis, then you can get much better result. 1.618 to the n. Okay, you can delete this term. Then this is not so difficult. Just look at here. Look at this size tree. Then here we have a clause of size 2. But here we also have a clause of size 2. Okay? So here you have a clause of size 2, but here you also have a clause of size 2. And you can prove that in any node in this search tree, you have at least one clause of size at most 2. Okay, at most 2. Then, this is only one exception. At the very beginning, you don't have any clause of size 2. But after that, in each node, you must have at least one clause of size at most 2. This is a property you can prove. Not very difficult. Here you have a clause size 2. Here you have a clause size 2, and here you have a clause of size 2, and so on and so forth. Then, of course, if you use this kind of, if you look at the same argument, by doing the same argument, you can get this formula, this recursion formula. And so the answer to this formula is 1.618 to the n. That is again much better than this. Okay. So this is the idea of backtracking. So the basic idea of backtracking is to find some structural property to reduce the search space. Okay. Then you can get this kind of a recursion formula, or that kind of recursion formula. Just solving that, then you can get a much better than 2 to the n. That is what we call exponential speed up. Okay, good. This is a backtrack. And then I'll show you local search. Local search is much more impressive. Okay, what is the basic idea? The basic idea of local search is, well, I'm not sure if this is a good explanation of local search, but my understanding is local search is something like okay, this is my understanding. This is my single word explanation of local search. That is random assignment plus local improvement. Okay, I'll show you what this means. Use the same example. Let us use the same example as before. So suppose that we are given that formula f. Then what we do is just a random assignment. Assign. Okay. So we just try random assignment. For example, x1 is equal to 0, x2 is equal to 0, x3 equal to 0, x1, x4 is equal to 1. Okay, just we flip coins, then we can get that random assignment. If that is the correct answer, if that is satisfying assignment like that, then we are happy because we are done. But maybe it's not the case. Then okay, x1, x2, x3 becomes false. The first clause the first clause, x1, x2, x3, all positive, then against that assignment, that clause becomes 0. That means that that assignment is not a satisfying assignment. That is not correct one. Then, we try local improvement. What does it mean? It means this guy becomes 0. 0, 0, 0. Okay. So what I'd like to do is try to make this guy true. This guy 1. By what? Of course, by changing one value from 0 to 1. Okay? So we change, for example, this value to 1. Then, unfortunately, the other guy becomes false. So this, whoops. X1 bar, X2, X4 bar. Wow, sorry. There is no such clause. I'm just adding one. Okay. X1 bar, X2, X4 bar. I'm sorry. Okay. So I changed value x1 because try to make this guy true. Then of course this guy becomes true, but unfortunately the other guy becomes false. Just we continue. Yes. Now we change this guy. So x1 is equal to 1, x2 is equal to 1, 3 is equal to 0, x4 is equal to 1, then done. Let's check. So x1 is equal to 1, the first guy is okay, the second guy is okay. x2 is equal to 1, x4 is equal to 1, so the third guy is okay. X1 is 1, okay, yeah, everything is okay. So we are done. We are lucky. Okay. So I'll show you our algorithm that is called SCH of formula F. SCH comes from the name of the person, name of the researcher who invented this system, this algorithm. Okay. It's not so important for you. So input. F is a 3CNN formula. Input is 3CNN formula. Now, the first step is just x equal A1, A2, AN. This is a random assignment. you choose just random assignment for value of x is value of x, then repeat 3n times. We have n variables. N variables. Then repeat 3n times the following. Select arbitrary false clause. False clause means a clause that is 0. That is false under the current assignment. Under the current assignment. Okay? Then select, again select one of the 3 variables at random. And flip it. Okay, so repeat 3n times these 2 steps. Select an arbitrary false clause. For example, x6, x7, x9. Now this guy is false. That means the current assignment is 0, 1, 0. Okay. Then select one of the 3 variables, x6, 7, 9, one of the 3 variables at random, and flip it. Flip means, of course, change 0 to 1 or 1 to 0. That means we select one of the 3 variables, say x9, and flip it. So the value of x9, 0 to 1. So now your current assignment changes by 1 bit. Just repeat. Repeat, repeat, repeat 3n times. Something's wrong. Something's wrong. Something's wrong. Sorry. Of course, at the beginning of each repetition, each repeat, of course, you have to check if the current assignment is the correct one. If the current assignment is a satisfying assignment, then you are done. So you just finish the procedure, just output yes. Otherwise, if the current assignment is not a satisfying assignment, of course, there is at least one clause that is false. Select an arbitrary false clause, arbitrary one of them, and then flip value of one variable. Okay. What we're gonna do? I'm gonna do is analysis. of this algorithm. Okay. If you run this algorithm once, then if you are very lucky, then maybe you can find a satisfying assignment. But probably you fail. You're gonna fail. That means after repeating this steps 3 times, you can't find satisfying assignment. That means all 3 times, all repetitions are false, failed. Okay, then the whole algorithm, of course, failed. So what I gonna, compute from now is success probability of this procedure, single run of this SCH. Okay. Okay, suppose that this is your final goal. So this is satisfying assignment. I don't know, something like x is equal to 1, 0, 0, 1, Okay. Suppose that this is a satisfying assignment, your final goal. Okay? And here, this is your current assignment. So we are here. We are here now. Your current assignment is something like x is equal to 0, 0, 1, 0, Okay. And this is k. And this is k minus 1. And this is k plus 1. What is this value? This is a Hamming distance. Hamming distance, meaning the number of bits that are different from your final goal. Okay, this is your final goal, maybe x star. This is your final goal, and this is your current position. Then the first bit is different. The second bit is also different. The third bit is also different. Wow. No. The first bit is different. The second bit is the same. The third bit is different. The fourth bit is different. So you just count the number of different bits. That is Hamming distance. That means if you are here now, meaning the k bits are different. K bits are different from your final goal. Okay. By single repetition, by a single flip, what can happen? By a single flip, what can happen? Okay. From here, you can go to here or here. You can approach to the final goal by 1 bit, or you can go to the opposite direction by 1 bit. With probability at least 1/3 with probability at most 2/3. This is important. This is really important. So, by doing single repetition of this procedure, you can go to good direction by 1 bit with probability at least 1/3. You can go to opposite direction, unfortunately, with probability at most 2/3. At most 2/3. Why? Why? Okay, if you can understand this, then after that, that's going to be a simple calculation. So most important point to understand is why. Okay? Now we are here. That this is not a satisfying assignment. Then we do have a clause. All three variables are bad. All three variables are bad. All three variables are bad is the three contribute to the Hamming distance, right? And this 0, 1, 0 all different from the final answer, right? Final answer should be 1, 0, 1. Oh no, I'm sorry. I'm sorry. Once again, the final answer should not be 0, 1, 0. At least 1 bit is different. Right? Because if the final answer is 0, 1, 0, then that is not satisfying assignment at all. That means the final goal should be at least 1 bit different. Okay? Suppose that only 1 bit is different. Then what is the probability you can hit it? At least 1/3. You can hit it, then you can approach to the final goal by 1 bit. You are lucky, then maybe you can change correct bit to the incorrect one. That means you can go to the bad direction with the probability 2/3. Okay? Once again, this is not satisfying assignment. There must be a clause. All bits are bad. All bits are 0. Then this assignment 0, 1, 0 should be different from the final goal. Because if final goal has a value 0, 1, 0, that is not satisfying assignment. At least 1 bit is different. If you can hit it, then you can go there. With probability, of course, 1/3, at least. Why at least? Because there may be 2 bits that are different from the final goal. Then your task is much, much easier. Right? Okay, now you understand this. Then okay, now you're here. You're here. Hamming distance of 5. Then, by doing this, you might be able to get here. Something like this. Okay? Probably, you might be able to get to the final answer from here. By following this kind of route, this kind of path. Then, okay, this is a bad direction. This is a good direction, good direction, good direction, bad direction, good, 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 good. Right? So your choice was good 1, 2, 3, 4, 5, 6, 7 times, and your choice was bad twice. Okay? Good choice. Twice. No, 7 times. Bad choice 2 times. What's the probability of your success? By following this path, this kind of path. That is pretty easy. Okay, your path is of length 9. Your path is of length 9, and out of 9 decisions, 2 decisions are bad. No, bad decision can happen 2/3, and 7 decisions are good. Each good decision can happen 1/3. So this is a probability. Success probability by following that kind of path. That kind of path means 7 times good choice, twice bad choice. Right? Pretty easy. We are also successful by following 9 times. No. Yeah, 9 times good choice, and 4 times bad choices. No, the probability with probability, this probability it is equal to, of course, 13 choose 4, and 1/3 9, 2/3 4. Okay, this is also successful. The length of path is 13 this time, and out of 13 choices, 4 are bad choice, 9 are good. It is also successful. We are also successful, maybe 11 and 6. So in general, we are successful with probability Okay. Okay. So in general, we are successful with this probability if your path length is k plus 2i. 2i. So that is I is equal to 2, and that is I is equal, no? Yes. That is I, for this, that I is equal to 2, and this I is equal to 4. Okay? Okay. Then what is your total success probability? Total success probability is, of course, to sum up by is obtained by summing up all these probabilities for I equal to okay. Just summing up this probability for I is equal to 0 to n. Why up to n? Well, because we repeat that procedure 3n times. This is not so important, actually. Okay? But, from now on, this is a simple calculation. So if you are tired, just maybe take a note, then maybe you can come back to the note after the class. From here, just a calculation. Okay? Right now, I'm going to do a very, easy approximation. Well, this is what? This is, of course, qk0 plus qk1 plus qk q plus qk n. Then, of course, this is a twist. qkk. So this is I'm gonna do this kind of a very rough approximation, but that is enough. Why that is enough? Because this is exponentially small. So this is exponentially small. So this is only n terms. So actually this is at least 1 over n. 1 over n times this value, at least. But as I said before, 1 over n can be ignored if this is exponentially small. Okay? So we can do this. And this is 3k, choose k. Okay. For here, use this formula. This is very convenient. This is a very convenient formula to evaluate binomial coefficient. Okay, and choose alpha n. Alpha is, of course, some constant less than 1. Okay, so and choose alpha n can be approximated by this this formula. Yeah, this equation. If you use this one for this part, then it's pretty easy to obtain this final value. It's pretty easy. We are done. So now, at the beginning, at the beginning of SH, process SH, you know, it's a you're gonna start with a random assignment. Okay, random assignment. Okay, random assignment. Then, okay, this is a final goal, and this is K. So what is the probability that you come here? The probability, this is X final goal. This is your current position. Your start point. This is your start point, K. I don't know. 0, 0, 1. This is your start point. Then the probability that your start point is here, namely, at the beginning, you are succeeded. You are successful from the beginning is what? 1/2 to the n. Okay? Because you have to be correct here, correct here, correct here, correct here. That means 1/2, 1/2, 1/2. That means 1/2 to the n. So you can be here with 1/2 to the n. Okay? Now you're here with the probability n to the k and 1/2 to the k and 1/2 to the n minus k is equal to n choose k 1/2 to the n. Right? Because that means Hamming distance is k means k bits are different. So you can choose k bits from n. That is n choose k. That k bits should be correct. That means 1/2 to the k. The other n minus k bits should be different. That means again 1/2 to the n minus k. The probability is here. The probability here. Okay. Then what is your total success probability? Just your success probability is just a summing up. Oh, okay. From here, your success probability is here. This 1/2 to the k. So the probability that you come here is this, and from here your success probability is here. So just just multiply by 1/2 to the k. Okay. So this part is here, and multiplied by 1/2 to the k is here. Just sum up for all k. For all k. But again, we have this simple approximation. Okay. We are going to do the simple approximation, just taking just one term. We ignore all other terms. This time, we choose k is equal to n over 3. K is equal to n over 3. Then this value is 3/4 to the n. 3/4 to the n. This is your success probability. By doing that SCH once. By doing that SCH once. Then repeat. By using a simple probability theory, just repeat that procedure 4/3 to the n times. Just the inverse value of this probability. Then you can enjoy high success probability. Maybe something like some constant or some polynomial n times 4/3 to the n. But once again, we can ignore those kind of polynomial coefficient. So the basic idea is just that you repeat SCH, that's the inverse of this success probability, then you can enjoy pretty high success probability. What is the value of this? The value of this is just exactly 1.334 to the n. Now that is again much better than 1.6 something to the n. And of course, it's much better than naive approach of 2 to the n. Wow. Yeah, this is the idea of local search. Surprisingly powerful. Surprisingly powerful. Okay. But of course, this is a very nice example for local search. Usually, it's not that simple. It's not that easy. That means you need to find this kind of very nice property, very nice mechanism for your local search. Okay. This problem, 3SAT, does have this kind of a good property. That is why local search is very, very powerful. Yeah. But okay, this is a good example for theory. But in practice, it's many people say local search is usually powerful. So your task is to find this kind of a good property, good property for one-step move. Just the basic idea is your position is here currently. Then you look at your neighbors. Then you go to somewhere. You go to some of your neighbors. Okay. The question is which neighbor is the best? Which neighbor is the best? Okay. That is the essence. That is the basic idea of local search. Okay, good.